Welcome to Ultimate Sleep Doctor. Tonight, we'll gently explore the vastness of beginnings. It began with an incredible burst of energy, a moment of pure creation, the Big Bang. Scientists believe the universe unfolded from an infinitesimally small point, expanding outwards at an astonishing rate. This expansion continues still, shaping galaxies and stars, a testament to fundamental forces. There's a humbling beauty in this idea that everything we see, everything we know, arose from a single extraordinary event. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. Just breathe, let your thoughts drift and find stillness within. Let's begin. Before the Big Bang, before anything we can truly grasp existed as space and time as we understand them, there was something different. It wasn't nothing, not entirely. Instead, it was a state of incredibly high energy density and temperature, a realm so extreme that our conventional physics, the laws that govern stars and galaxies, simply ceased to apply. Scientists, after decades of pondering the most fundamental questions about the universe's beginning, developed theoretical models to describe this period, a period they've affectionately termed inflation. Inflation wasn't a regular expansion. It was a mind-bogglingly rapid exponential growth, an instant cosmic fireworks display driven by a force we still don't fully comprehend. The idea for inflation emerged in the early 1980s, largely thanks to the work of Alan Guth and Andre Lind. They were wrestling with several puzzling observations about the universe, primarily the cosmic microwave background, CMB, radiation, that faint afterglow of the Big Bang that permeates the entire observable universe. The CMB had a remarkable uniformity, meaning it was incredibly smooth and consistent across vast distances. This uniformity presented a problem. According to standard Big Bang theory, density fluctuations, tiny variations in the early universe's density, should have grown over time, eventually seeding the formation of galaxies and large-scale structures. But the fluctuations seen in the CMB were far too small to have grown into the structures we observe today. Something had to have smoothed things out, erasing these initial ripples. Inflation offered a beautiful solution. It proposed that for a tiny fraction of a second, an instant measured in less than a trillionth of a second, the universe underwent an extraordinary period of expansion, increasing in size by a factor of at least 10^26. That's a 1 followed by 26 zeros. To put that into perspective, it's like taking a pea and expanding it to the size of our solar system, then expanding it to the size of our galaxy, and then to the size of the observable universe, all in the blink of an eye. This isn't a gentle stretching. It's an explosive, almost instantaneous transformation. The driving force behind this inflation is a hypothetical field called the inflaton. Think of the inflaton as a kind of energy field that permeated all of space in the very early universe. This field possessed a negative pressure, a sort of tension, that acted like a repulsive force. This negative pressure is crucial. According to Einstein's theory of general relativity, energy and pressure contribute to the curvature of space-time. Positive energy and pressure cause spacetime to curve inward, leading to gravity. But negative pressure, as experienced by the inflaton, acted like a repulsive force, pushing spacetime outward. Imagine a balloon. As you blow it up, the rubber stretches and the surface area increases. Now, imagine the rubber itself is imbued with a special property, a property that causes it to stretch even faster, exponentially faster as it's inflated. That's a rough, albeit simplified, analogy for the inflaton's effect on spacetime. The negative pressure generated by the inflaton caused spacetime to expand at a rate faster than the speed of light. Crucially, it didn't violate Einstein's theory of special relativity, which states that nothing can travel through spacetime faster than light. Instead, spacetime itself was expanding, carrying everything along with it. This rapid expansion smoothed out any initial quantum fluctuations, tiny uncertainties in the energy density that might have existed. These fluctuations, magnified by the exponential expansion, became the seeds of all the structures we see today. Galaxies, clusters of galaxies, and the large-scale distribution of matter in the universe all originated from these stretched-out quantum ripples. The inflaton essentially acted as a cosmic eraser, removing any imperfections and setting the stage for the subsequent, slower expansion that we observe today. Furthermore, inflation predicts a specific pattern in the CMB radiation, a nearly scale-invariant spectrum of temperature fluctuations. This means that the tiny temperature variations observed in the CMB were, on average, equally distributed across all wavelengths, from the shortest radio waves to the longest radio waves. This exquisite uniformity is one of the strongest pieces of evidence supporting the inflationary theory. The models also predict something called tensor, or gravitational waves, ripples in spacetime itself, generated during the inflationary period. These waves, produced by the rapid stretching of spacetime, would have been imprinted on the CMB. Scientists are actively searching for these gravitational waves, and recent observations from the BICEP-2 experiment, though initially controversial, provided tantalizing hints of their existence. Detecting these waves would provide direct evidence for inflation and further solidify our understanding of this extraordinary epoch. It's important to remember that inflation is still a theoretical model, a framework for understanding the very beginning of the universe. We haven't directly observed the inflaton or the gravitational waves it produced. However, the evidence supporting inflation is mounting, and it remains the most compelling explanation for the CMB's uniformity and the large-scale structure of the universe. It's a story of exponential growth, quantum seeds, and a universe shaped by a force we are still striving to understand. The universe, still incredibly young, was a chaotic, opaque soup. It wasn't dark, not in the way we now understand darkness. Instead, it was a dense, scorching plasma, a swirling mix of electrons, protons, and photons, constantly bouncing into each other. These photons, the fundamental particles of light, couldn't travel very far. Every time a photon tried to move, it immediately collided with an electron, losing its energy and disappearing. This constant scattering made the universe completely opaque, like looking through a thick fog. It was impossible to see anything beyond the immediate vicinity. This intense heat, born from the initial expansion, was the dominant characteristic of the early universe, a state of continuous energetic interaction. For countless years, this state remained unchanged. The expansion of the universe continued, but the fundamental properties of the plasma, its density, temperature, and the way photons interacted with it, didn't shift dramatically. Scientists, like a diligent detective, began to consider the possibility that there might be evidence of this early, hot phase hidden within the universe's current state. The crucial question was, if the universe had been expanding, hadn't this initial heat had to dissipate somehow? The prevailing thought at the time was that this heat would have quickly spread outwards, much like heat radiating from a hot stove. But the expansion rate was key. It was far too rapid for this heat to simply disperse. The breakthrough came unexpectedly in 1964, thanks to a team led by Arno Penzias and Robert Wilson at Bell Labs. They were working on a project to improve the sensitivity of a microwave antenna designed to detect signals from satellite communications. While calibrating the instrument, they detected a persistent, low-level microwave signal, a hiss, that they couldn't identify or eliminate. It wasn't from any terrestrial source. It wasn't from weather patterns or human-made equipment. It was ubiquitous, appearing equally in all directions. Initially, they were frustrated, bordering on defeated. They meticulously checked their equipment, searched for sources of interference, even considered it a sign of a fundamental flaw in their instrument. However, their colleague, Jerry Ale, noticed a crucial observation. The signal remained remarkably constant, regardless of the time of day or the position of the antenna. This consistency, combined with the signal's uniform distribution across the sky, began to suggest a very strange possibility. Further investigation, spurred by the work of physicist George Gamow, who had long theorized about the leftover heat from the Big Bang, led to a truly astonishing conclusion. Gamow and his colleagues realized that if the universe had been expanding from an incredibly hot and dense state, and if this expansion had continued for billions of years, the wavelengths of the photons originally emitted would have been stretched along with the expansion. This stretching, a process called cosmological redshift, is a fundamental principle of cosmology. Redshift, in essence, means that the light waves are stretched out, shifting them towards the red end of the spectrum, just like how the sound of a siren changes pitch as it moves away from you. This stretching wasn't just a change in color, it dramatically altered the energy of the photons. The original, high-energy photons from the Big Bang, having traveled for 13.8 billion years, had been stretched to incredibly long wavelengths, specifically into the microwave region of the electromagnetic spectrum. The discovered microwave signal was, in fact, the very remnant of this stretched radiation, the cosmic microwave background radiation, or CMB for short. It's like a ghostly echo of the Big Bang itself. The CMB is incredibly uniform in temperature, about 2.7 Kelvin, or minus 270.45 degrees Celsius. This uniformity is remarkable, considering the CMB has traveled across the entire observable universe. Tiny fluctuations in the temperature of the CMB, detected through increasingly sensitive instruments, provide a snapshot of density variations in the early universe, the seeds of galaxies and larger structures we see today. Scientists analyze the patterns of temperature variations in the CMB using techniques like polarization, examining how the microwaves are oriented. These patterns are incredibly complex, but they reveal the geometry of the universe, whether it's flat, curved, or something in between. The CMB data strongly supports the idea that our universe is flat. Furthermore, the CMB's existence provides incredibly strong evidence for the Big Bang theory. It's not just a theoretical prediction, it's a direct observation of the universe's infancy. It's a tangible piece of the cosmic puzzle, a historical record etched in the radiation that permeates all of space. The CMB isn't just a signal, it's a confirmation. It's a beautiful and profound testament to the immense power and elegance of the universe's origin story. Studying the CMB continues to be a primary focus in cosmology today. Each new generation of telescopes and detectors allows us to probe the CMB with ever-increasing precision, unlocking even more secrets about the universe's past and shaping our understanding of its future. The cosmic microwave background radiation, born from the afterglow of the Big Bang, is, in its own quiet way, speaking to us across the vast expanse of time. The very first moments after the Big Bang weren't just filled with energy, a swirling, hot soup of photons and fundamental particles. There was also matter, but not in the way we experience it today. It was a profoundly unequal situation, a cosmic imbalance that set the stage for everything that followed. Scientists have long wrestled with the question of why there's so much more matter than antimatter in the observable universe. This is the puzzle of baryogenesis. The initial conditions of the Big Bang, as we understand them through models of inflation and the resulting expansion, suggested that equal amounts of matter and antimatter should have been created. When photons and fundamental particles collided in those first fractions of a second, they would have annihilated each other, converting entirely into energy photons again. The universe should have been a blank slate, devoid of anything we recognize as stuff. Yet when we look around us at stars, planets, and ourselves, we see a universe overwhelmingly dominated by matter. It's a remarkable and incredibly perplexing observation. The standard model of particle physics initially offered a simple, though ultimately insufficient, explanation. It predicted that matter and antimatter should have been created in equal quantities. However, the simple mathematics didn't match reality. There was a significant and unexplained surplus of matter. This discrepancy is often referred to as the baryon asymmetry. Scientists began to explore potential mechanisms, processes that could have preferentially generated matter. One of the leading ideas revolves around a process called CP violation, a subtle asymmetry in how particles interact. CP stands for charge parity. Charge refers to the electric charge of a particle, while parity describes how a system behaves under spatial inversion, mirroring. In the standard model, CP violation exists, but it's incredibly weak. The amount of CP violation present isn't nearly enough to account for the observed baryon asymmetry. However, theorists investigated whether there were additional CP violating interactions that operated in the early universe, interactions that were stronger and more effective. These hypothetical interactions often involved heavy, short-lived particles, particles far heavier than anything we've directly observed. These particles, if they existed, would have briefly appeared in the extremely hot and dense conditions of the early universe. They would have then undergone processes that favored the production of matter over antimatter. One prominent idea involves hypothetical particles called Majorana fermions. These are particles that are their own antiparticles. When Majorana fermions interact, they can generate a small asymmetry. Another possibility focuses on the decays of these heavy particles, processes where they transform into lighter particles, again with a slight preference for matter. The key is that these interactions wouldn't have been random. They would have been governed by the subtle imbalances within the fundamental laws of physics. It's like a cosmic lottery, where a tiny probability, incredibly small but significant, consistently tipped the scales in favor of matter. Another area of research explores leptogenesis. This concept suggests that the baryon asymmetry wasn't directly generated, but rather arose as a byproduct of an asymmetry in the number of leptons, fundamental particles like electrons and neutrinos, and their corresponding antiparticles. The creation and annihilation of leptons and antileptons could have generated a lepton asymmetry, which would then have subsequently produced the observed baryon asymmetry through a process called sphalurin mixing. This mixing, a complex interaction, converts baryon and lepton number, effectively transforming the imbalance. The search for evidence of baryogenesis is incredibly challenging because the processes involved occurred in the very earliest moments of the universe, before the formation of stable atoms. The universe cooled and expanded, diluting any initial imbalances. Furthermore, the energy scales involved are far beyond what we can currently recreate in particle accelerators. Despite these difficulties, scientists are pursuing several avenues of investigation. They are analyzing data from the cosmic microwave background, CMB, looking for subtle signatures of baryogenesis. The CMB, that leftover heat from the Big Bang, could potentially contain faint traces of the processes that generated the baryon asymmetry. Additionally, theorists are working to refine models of baryogenesis, exploring new particles and interactions. It's possible that our understanding of the fundamental laws of physics, particularly at extremely high energies, is incomplete. Perhaps there are yet undiscovered forces or particles that played a crucial role in shaping the imbalance we observe today. The question of baryogenesis remains one of the most profound mysteries in cosmology. It highlights the delicate balance between the laws of physics and the initial conditions of the universe. Solving this puzzle is not just about understanding the origin of matter, it's about understanding the very fabric of reality. It's a story of incredibly small probabilities creating vast differences, a testament to the power of physics in shaping the cosmos. The ongoing research, combining theoretical models with experimental data, offers the potential to unlock one of the universe's greatest secrets, the reason why we exist. And perhaps, one day, we'll fully understand the origin of this remarkable asymmetry, this fundamental imbalance that defines our universe. The universe, as we understand it, began with an unimaginable burst of energy. The inflation that followed, a period of exponential expansion driven by the energy of space itself, had already sculpted the very fabric of space-time. But even that incredible expansion couldn't fully explain what existed in the immediate aftermath, the nanoseconds after the Big Bang. To truly grasp this period, we need to talk about a state of matter so extreme, so profoundly different from anything we experience today, that it's almost impossible to picture. We're going to delve into the realm of the quark-gluon plasma. At the very beginning, the universe wasn't a place of particles like electrons and protons, neatly arranged and bound together. It was a chaotic soup, a roiling, shimmering sea of fundamental particles. Specifically, it was a dense, superheated environment filled with quarks and gluons. These aren't the familiar particles found in everyday matter. They are the most basic building blocks of matter, the kind of stuff that exists at the core of atomic nuclei. However, in this primordial state, they weren't confined within these structures. They were free, moving at speeds close to the speed of light, constantly colliding and interacting with each other. The energy density during this epoch was absolutely colossal. It was so intense that the very concept of temperature as we know it breaks down. It wasn't simply hot. It was in a state of extreme thermal excitation. Every quark and gluon possessed an enormous amount of kinetic energy. The pressure was equally astounding, far exceeding anything found in the densest stars. This isn't like heat from a fire. It's a fundamental energy, a consequence of the universe itself being incredibly young and incredibly small. Scientists describe this state as a quark-gluon plasma. The term plasma refers to a gas where the particles are ionized, meaning they've lost their electrons and are free to move around. In this case, however, the plasma isn't made of ordinary atoms. Instead, it's composed entirely of quarks and gluons, constantly interacting through the strong nuclear force, the force that binds the nucleus of an atom together. This strong force is far more powerful than the electromagnetic force that governs the interactions between electrons and nuclei. And it's what makes the quark-gluon plasma so incredibly difficult to study. Imagine trying to study a constantly shifting, incredibly hot cloud of particles, where every collision generates new particles and changes the conditions instantaneously. The interactions are happening at nearly the speed of light, making it exceptionally difficult to track individual particles. The very act of attempting to measure the plasma would disrupt it, creating new interactions and further complicating the picture. This is a significant challenge for researchers. Detecting and studying the quark-gluon plasma is a remarkable feat of scientific ingenuity. Scientists haven't been able to directly observe this state in its natural form. It simply doesn't exist stably outside of the extreme conditions of the early universe. Instead, they've developed powerful particle colliders, like the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory and the Large Hadron Collider, LHC, at CERN. These machines accelerate heavy ions, typically gold or lead nuclei, to incredibly high speeds and smash them together. These collisions recreate, for a fleeting moment, the conditions that existed in the early universe. The energy released in the collision is so great that it momentarily creates a tiny, localized version of the quark-gluon plasma. Scientists then analyze the particles produced in these collisions, looking for specific signatures, patterns in their behavior, that indicate the presence of this exotic state of matter. These signatures include the creation of certain heavier particles, like photons, particles of light, that don't normally exist at such high temperatures. The analysis of these collisions provides crucial evidence supporting the theory of the quark-gluon plasma and allows scientists to probe the properties of this state. They can measure things like the temperature, density, and viscosity of the plasma, offering a window into the fundamental physics of the universe in its infancy. The results from these experiments have confirmed many theoretical predictions and have pushed the boundaries of our understanding of particle physics. It's important to understand that the quark-gluon plasma wasn't a permanent state. As the universe expanded and cooled, the energy density decreased, and the quarks and gluons eventually began to combine to form hadrons, particles like protons and neutrons. These hadrons then went on to combine to form the nuclei of atoms, ultimately leading to the formation of the stars and galaxies we see today. The study of quark-gluon plasma is therefore not just about understanding the very beginning of the universe. It's also about understanding the processes that led to the formation of the matter that makes up everything we see around us. It's a testament to the power of scientific inquiry and the ability of humans to explore the most extreme conditions and unravel the deepest mysteries of the cosmos. It's a remarkable story of recreating a moment in time, a fleeting glimpse into the universe's first moments, and a continuing quest to understand the origins of all things. The universe, just moments after the Big Bang, wasn't the neatly organized place we see today. It was an incredibly hot, dense soup, far beyond anything we can truly comprehend. This soup wasn't just made of energy. It contained the fundamental building blocks of matter, particles constantly zipping around in a frantic dance. For the first tiny fraction of a second, the universe existed primarily as a quark-gluon plasma, a swirling sea of quarks and gluons, the force carriers of the strong nuclear force. But this state wouldn't last. As the universe rapidly expanded and cooled, these fundamental particles began to interact in complex ways, driven by the laws of quantum mechanics. The conditions were extreme. Energy was converted directly into matter, a process described by Einstein's famous equation, E equals mc2, where energy E is equal to mass m, multiplied by the speed of light squared c2. This wasn't a gentle transition. It was a violent, chaotic transformation. Quarks, the most basic constituents of protons and neutrons, weren't happily bound together. They were constantly being created and annihilated, a relentless cycle of existence fueled by the immense energy of the early universe. At these temperatures, the strong nuclear force, which normally holds quarks together within protons and neutrons, was incredibly powerful. However, it wasn't strong enough to permanently bind these quarks. Instead, quarks and gluons were constantly colliding, scattering off each other and being absorbed and re-emitted. This process was governed by quantum fluctuations, tiny, temporary disturbances in the energy field, driven by the uncertainty principle. These fluctuations, though incredibly brief, were significant enough to create and destroy quarks and gluons, constantly changing the composition of the plasma. As the universe continued to expand and cool, a crucial phase began: the formation of hadrons. Hadrons are composite particles made up of quarks and gluons, and the first stable hadrons were mesons. Mesons are made of a quark and an antiquark, a perfect symmetry disrupted by the fundamental imbalance in the universe. But the creation of protons and neutrons, the building blocks of atomic nuclei, was a more intricate process. Protons are formed from 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. These specific combinations were favored due to the probabilistic nature of quantum interactions. It wasn't that these combinations were guaranteed to form, but the quantum mechanical calculations showed that, given the conditions, they were the most likely outcomes. This probability wasn't predetermined. It was the statistical result of countless particle interactions. The formation of these particles involved a process called hadronization. Imagine a single up quark, buzzing with energy, encountering a region of space where the temperature and density are just right. It doesn't simply appear. It's the result of a quantum tunneling event. Quantum tunneling is a phenomenon where a particle can pass through a barrier, even if it doesn't have enough energy to overcome it classically. In this case, the up quark effectively tunnels through the energy barrier, appearing in a region where it combines with another down quark to form a neutron. The down quarks were formed through a similar process, again, dictated by quantum fluctuations. These fluctuations created regions of high energy where down quarks could briefly exist before being annihilated. The interactions between quarks and gluons were not simple collisions. They were mediated by the exchange of virtual particles, particles that exist for incredibly short periods, governed by the uncertainty principle. These virtual particles, acting as messengers, facilitated the force interactions between the quarks. As the universe cooled further, the rate of these interactions slowed down. The energy available to create new particles diminished, and the probability of forming protons and neutrons increased. However, it wasn't a perfectly smooth transition. There were still many regions of the universe where quarks and gluons were intensely interacting, leading to the formation of exotic particles and short-lived states. The entire process was a complex dance of creation and annihilation, a testament to the fundamental laws of quantum mechanics. The exact proportions of protons and neutrons that formed in the early universe are still a subject of ongoing research. Subtle differences in the composition at this stage influenced the subsequent formation of the first atomic nuclei, laying the groundwork for the evolution of the elements we see today. The universe, in its infancy, was steadily building its foundational components, particle by particle, governed by the most fundamental rules of reality. This process continued for several minutes, shaping the very structure of the cosmos. Ultimately, the formation of protons and neutrons represents one of the most astonishing transformations in the history of the universe, a pivotal moment marking the beginning of the creation of heavier elements and the eventual emergence of stars and galaxies. The universe, just moments after the Big Bang, wasn't a smooth, homogeneous soup as some might initially picture. Instead, it was a violently turbulent sea, a swirling cauldron of energy and newly formed particles. While the initial conditions were dominated by incredibly high temperatures, as this energy began to dissipate, it left behind a subtle but incredibly important legacy: cosmic magnetic fields. These fields weren't created in a single, dramatic event, but rather emerged through a complex interplay of processes occurring within the young universe. One of the primary mechanisms for their generation was the interaction of charged particles, primarily electrons and protons, with the intense ultraviolet radiation that filled the space. This radiation, a remnant of the Big Bang itself, possessed a surprising property. It was polarized. This means that the light waves weren't just oscillating up and down, but also had a slight twist to them, a tiny magnetic field embedded within the light itself. As electrons and protons zipped through this polarized radiation, they acted like tiny antennas, interacting with the magnetic field. This interaction caused them to spiral around the field lines, much like a tiny compass needle aligning itself with the Earth's magnetic field. This spiraling motion isn't merely a passive response. It's an active process involving the transfer of energy and momentum between the particles and the magnetic field. The more intense the radiation, the stronger the magnetic field became, and the more pronounced the spiraling motion. This process wasn't uniform across the universe. Regions with higher densities of charged particles, particularly near the early cosmic structures forming, experienced stronger magnetic fields. These initially weak fields rapidly amplified through a process known as dynamo action. Dynamo action is essentially a self-sustaining feedback loop. As charged particles spiraled around the magnetic field lines, they were accelerated, and this acceleration generated electromagnetic waves, radio waves, in this case, which then acted to further accelerate the charged particles. It's a cascading effect, a cosmic dance of energy and momentum that built up the magnetic fields over time. The distribution of these magnetic fields wasn't random. They weren't just evenly spread throughout space. Instead, they formed large-scale structures resembling a tangled web, now known as the cosmic magnetic web. These filaments and nodes of magnetic field concentration were intimately linked to the formation of the first galaxies and larger cosmic structures. The magnetic fields acted as seeds, guiding the flow of matter and influencing the way gas and dark matter coalesced under the gravitational pull of the universe. It's thought that the magnetic fields helped to channel the flow of primordial hydrogen and helium, directing it towards regions where gravity was particularly strong. ultimately contributing to the formation of the first stars and galaxies. Furthermore, the magnetic field significantly impacted the movement of the charged particles themselves. The spiraling motion caused by the magnetic forces isn't just a visual effect. It dramatically altered the paths these particles took. Instead of moving in straight lines as they would in a region free of magnetic fields, these charged particles were forced to follow curved trajectories, looping and swirling around the field lines. This chaotic movement wasn't entirely random, however. The direction of the spiral motion, the pitch of the spiral, was closely related to the particle's velocity. Faster particles took tighter spirals, while slower particles followed more elongated paths. The influence of these cosmic magnetic fields extended far beyond the formation of large-scale structures. Within the first galaxies, these fields played a crucial role in regulating the behavior of the plasma, the ionized gas, that filled these nascent galaxies. The magnetic forces exerted a pressure on the plasma, resisting its expansion and helping to maintain the structure of the galaxies. This magnetic pressure is still a factor today, influencing the shape and dynamics of galaxies across the universe. Interestingly, simulations show that the magnetic fields help to suppress the violent mergers of galaxies that might otherwise have occurred, smoothing out the process and allowing for a more gradual evolution of the cosmic structure. As the universe continued to expand and cool, the magnetic fields also underwent a transformation. The spiraling motion of the charged particles slowed down, and the magnetic fields themselves became more stable. However, they never completely disappeared. Even today, faint traces of cosmic magnetic fields can be detected across the universe, providing a tangible link to the very early moments of the Big Bang. These residual fields, detected by satellites observing radio waves emitted by electrons spiraling around magnetic fields, are a powerful reminder of the complex and dynamic processes that shaped the universe we observe today. The study of cosmic magnetic fields is a fascinating window into the infancy of the universe, a way to reconstruct the conditions that existed just fractions of a second after the Big Bang. Understanding these fields helps us to piece together the story of how the universe evolved from a hot, chaotic plasma to the complex, structured cosmos we inhabit now. Their existence is a testament to the fact that even in the most violent and energetic environments, subtle forces like magnetism play a profound role in shaping the ultimate destiny of the universe. The echoes of the Big Bang, carried on the waves of magnetic fields, continue to resonate throughout space and time. The universe, just moments after the Big Bang, was quite the smooth, expanding void we often picture. It was a tremendously energetic, incredibly dense soup of fundamental particles, quarks, leptons, photons, all jostling and interacting in a state of chaotic equilibrium. But something was missing. Observations of the cosmic microwave background, the afterglow of the Big Bang, revealed a surprising anomaly. The patterns of temperature fluctuations within this background radiation hinted at a gravitational influence far greater than could be accounted for by the visible matter, the protons, neutrons, and eventually, the atoms that we know existed. This discrepancy pointed to the existence of something unseen, something that profoundly shaped the early universe, something we now call dark matter. Initially, the idea of dark matter was quite radical. It wasn't that we were simply unaware of galaxies or nebulae. The evidence suggested a fundamentally different substance permeated space, exerting a gravitational pull that affected the behavior of everything within it. Several hypotheses began to emerge, each grappling with the nature of this mysterious component. One prominent theory proposed weakly interacting massive particles, or WIMPs. These hypothetical particles were thought to interact with ordinary matter only through gravity and possibly the weak nuclear force, explaining why they are so difficult to detect. The idea was that in the immediate aftermath of the Big Bang, when the universe was incredibly hot and dense, WIMPs could have been abundant, constantly interacting and influencing the distribution of matter. Their gravitational effects would have been crucial in halting the rapid expansion that followed the initial inflationary period, allowing for the formation of larger structures. Another leading hypothesis suggested that dark matter might consist of axions, extremely light and weakly interacting particles. Axions were proposed to solve a puzzle in particle physics, the strong CP problem, and it turned out they could also provide a compelling explanation for the existence of dark matter. These axions, even if lighter than WIMPs, would have had enough mass to generate the necessary gravitational force to shape the early universe. The key difference was their incredibly weak interaction with ordinary matter, making detection incredibly challenging. Scientists began designing experiments, deep underground detectors shielded from cosmic rays, hoping to capture the faint signal of axions passing through the Earth. The distribution of dark matter in the early universe was theorized to have been far from uniform. Instead, it likely formed large-scale clumps and filaments, acting as gravitational seeds that attracted ordinary matter. These clumps aren't like the familiar dark matter halos surrounding galaxies today. In the early universe, they were much more extensive and influential, stretching across vast distances. These structures would have played a critical role in the formation of the first stars and galaxies. Without this initial scaffolding provided by dark matter, the universe would have remained a much smoother, less structured environment, a far less conducive one for the formation of complex objects. Evidence for dark matter's presence extends beyond the subtle anomalies in the cosmic microwave background. Observations of galaxy clusters provide particularly strong support. Clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. The velocities of the galaxies within these clusters are far too high to be explained solely by the gravity of the visible galaxies. The galaxies are moving so quickly that, according to the laws of gravity as we understand them, they should have long ago flown apart. The only way to explain their stability is to postulate the existence of a substantial amount of unseen mass, dark matter, holding them together. Furthermore, gravitational lensing, the bending of light by massive objects, offers another compelling line of evidence. When light from a distant galaxy passes near a massive foreground object, Like a galaxy cluster, the light is bent and distorted. The amount of distortion is directly related to the mass of the intervening object. Measurements of gravitational lensing effects consistently show that the mass required to produce the observed distortions is significantly greater than the mass of the visible matter. Computer simulations of the early universe, incorporating the presence of dark matter, have proven remarkably successful in recreating the large-scale structure we observe today, the cosmic web of filaments and voids. These simulations demonstrate that dark matter's gravitational influence was absolutely fundamental to the formation of this structure. Without it, the universe would be an unrecognizable place, devoid of the galaxies, clusters, and voids that define its current form. The precise nature of dark matter remains one of the biggest mysteries in modern cosmology. While WIMPs, axions, and other candidates have been investigated extensively, none has yet been definitively detected. However, ongoing research, including large-scale surveys of the universe, direct detection experiments, and collider searches, continues to refine our understanding and bring us closer to unlocking the secrets of this elusive substance. It's a story of profound implications for our understanding of the universe's origin, evolution, and ultimately, our place within it. The ongoing quest to understand dark matter truly represents a frontier of scientific exploration, pushing the boundaries of human knowledge and promising to revolutionize our perception of the cosmos. The universe, in its immediate aftermath, was a seething, dense soup. It wasn't a static, empty space, but a violently churning ocean of photons and charged particles, mostly electrons and protons, constantly interacting. This early universe, less than 380,000 years after the Big Bang, was opaque, utterly unable to transmit light. Each time a photon tried to travel, it immediately slammed into a free electron, scattering in a random direction. It was like trying to see through a thick fog, or perhaps attempting to shine a flashlight into a room full of bouncing balls. The light was relentlessly absorbed and re-emitted, creating a continuous thermal glow, a cosmic background radiation, though incredibly faint and distorted by the constant collisions. This radiation was the dominant feature of the universe at this time, a sort of primordial haze. The energy density was astonishing. It wasn't just about the raw energy released in the Big Bang. It was the energy inherent in the continual creation and annihilation of particle-antiparticle pairs, the ongoing bounce of photons. The universe was, in essence, radiating intensely. The temperature was staggering, roughly 10,000 Kelvin. This immense heat was driving the chaotic dance of particles. As the universe continued to expand, it also continued to cool. This expansion was not a gentle stretching. It was a furious acceleration, fueled by something we now call dark energy. This expansion was the key ingredient in the unfolding drama that would ultimately lead to the transparency we observe today. The rate of expansion directly affected the density of the universe. As it expanded, the density decreased. The crucial process that fundamentally altered the universe's state began with a subtle shift in the balance of energy. The expansion was increasing, and with it, the rate at which photons were being created. but the density of free electrons was not increasing at quite the same pace. This difference in expansion rates was what instigated the final stage of the universe's evolution. The temperature continued to drop, now approaching 3000 Kelvin. At this point, a remarkable thing started to happen. The photons began to win. The expansion was now overwhelming the effects of the electron density. The photons began to travel vast distances without being constantly scattered. They were, for the very first time, experiencing a relatively unimpeded journey through space. This period, lasting approximately 370,000 years after the Big Bang, is known as recombination. The name is somewhat misleading. There was no single dramatic event. It was a gradual, ongoing process. However, the term signifies the moment when the universe became transparent to electromagnetic radiation, specifically visible light. During recombination, the universe's temperature had cooled sufficiently for protons and electrons to combine. These particles, driven by the relentless expansion, fused together to form neutral hydrogen atoms. Before this point, nearly all the hydrogen was in the form of free protons and electrons. This was a fundamental shift. The formation of neutral hydrogen is the core of the recombination story. Hydrogen, the simplest atom, is incredibly stable, with a very high energy level. When a proton and an electron combine, they form a stable hydrogen atom, releasing a tiny amount of energy in the process. This released energy appeared as photons of light, the very first photons that could travel freely through space. It's important to understand that the photons released during recombination weren't the first light in the universe. Light had been emitted during the initial moments of the Big Bang and subsequently scattered repeatedly before recombination. But these earlier photons were vastly different. They were high energy, extremely hot, and shifted towards the ultraviolet end of the spectrum. The photons released during recombination, however, were significantly cooler and shifted towards the red end of the spectrum. This is why we refer to this period as the last scattering surface. They represent the oldest light in the universe, the afterglow of the Big Bang itself. This light, redshifted by the expansion of the universe, now permeates all of space, detectable today as the cosmic microwave background, CMB. The CMB isn't a uniform glow. It has slight temperature variations, tiny fluctuations imprinted on the light at the time of recombination. These fluctuations represent the seeds from which large-scale structures, galaxies and clusters of galaxies, eventually grew. They are, in essence, the first ripples in the fabric of space-time. Once recombination occurred, the universe transitioned from an opaque, chaotic haze to a relatively transparent environment. Galaxies could begin to form, and the universe could evolve according to the laws of physics, largely unimpeded by constant scattering. The existence of the CMB offers a unique window into the infant universe, a snapshot of the universe as it was 380,000 years after the Big Bang, a direct consequence of that pivotal moment of recombination. It's a legacy of the Big Bang, and a reminder of the incredible processes that have shaped the cosmos we observe today. The universe, just moments after its explosive birth, wasn't a smooth, uniform soup of energy. It possessed a subtle, almost imperceptible imperfection. Tiny variations in density, minuscule differences in how much energy was concentrated in certain regions, existed throughout the incredibly hot, rapidly expanding space. These weren't like ripples in a pond. They were inherent characteristics of the early universe's quantum fluctuations. These fluctuations stemmed from the inherent uncertainty in the laws of physics at that extreme energy level, a consequence of the universe's infancy. The universe was essentially brimming with tiny, random fluctuations in density, like invisible hills and valleys scattered across an immense, expanding landscape. These initial density fluctuations weren't entirely random, though. They possessed a slight statistical bias. Slightly more regions were a bit denser than average, and slightly fewer were less dense. This wasn't a deliberate design. It's a feature of how quantum fields behave when disturbed. However, this bias was crucial. It provided the seeds for the structures we observe today: galaxies, clusters of galaxies, and the vast cosmic web. The greater the energy of the early universe, the more significant these initial fluctuations were, and the greater their potential to influence the universe's evolution. As the universe continued to expand, driven by the relentless force of the Big Bang, these density fluctuations began to grow. This growth wasn't a rapid, instantaneous process. It was a slow, gradual amplification, driven by a principle known as gravitational instability. Gravity, the fundamental force of attraction between all matter, acted on these slightly denser regions. Because these regions were already a bit more crowded with energy, they exerted a stronger gravitational pull on their surroundings. This stronger gravity caused more and more energy, originally spread out evenly, to flow towards these denser areas. It's like a snowball rolling down a hill. It gathers more snow as it goes, growing larger and larger. Similarly, the denser regions attracted more and more energy from the surrounding space, increasing their density even further. This, in turn, amplified their gravitational pull, attracting even more energy. It was a positive feedback loop, a runaway process of gravitational growth. The expansion of the universe, while stretching space itself, didn't diminish the effectiveness of gravity. In fact, it actually enhanced it. As space expanded, the density of matter, and therefore the strength of gravity, remained relatively constant. This is because the density of the universe was decreasing with expansion, but the gravitational force, related to the amount of matter, was also decreasing in a similar way. It's a somewhat counterintuitive concept, but it's essential for understanding how these tiny fluctuations grew into the grand structures we see today. Over billions of years, this process continued. The denser regions, now vastly larger and more concentrated, continued to attract more and more matter, dark matter and ordinary matter, falling into their gravitational wells. Simultaneously, the less dense regions gradually lost matter to the surrounding space, diminishing their gravitational influence. The universe was effectively sorting itself, separating into regions of high density and low density, guided solely by the force of gravity. It's important to remember that dark matter played a pivotal role in this process. Because dark matter doesn't interact with light, it wasn't affected by the recombination event that made the universe transparent. This meant that dark matter's gravity could act unimpeded, accelerating the growth of density fluctuations and shaping the large-scale structure even before ordinary matter could significantly contribute. Ordinary matter, however, was subject to the recombination process, which altered the way it interacted with photons, slowing down its contribution to the gravitational growth somewhat. As the universe continued to cool, the growth of density fluctuations slowed down. However, it never completely stopped. Even today, on the largest scales, subtle variations in the density of the universe's distribution are still observable, representing the faint echoes of those initial, tiny fluctuations from the Big Bang. These fluctuations are imprinted in the cosmic microwave background radiation, the afterglow of the Big Bang, as slight temperature variations. Scientists analyze these variations to reconstruct the conditions of the early universe and understand how the universe's structure formed. The resulting structure, the cosmic web, is a breathtakingly complex network of filaments and voids. Giant filaments, hundreds of millions of light years long, connect clusters of galaxies, while vast voids devoid of galaxies separate them. Galaxies are typically found at the intersections of these filaments, drawn together by the relentless pull of gravity. This cosmic web isn't a random arrangement. It's a direct consequence of those initial, tiny density fluctuations, the seeds sown in the extreme conditions of the early universe. The formation of galaxies and clusters of galaxies isn't a singular event, but a protracted, ongoing process. Galaxies still merge and interact, their shapes and trajectories influenced by the gravitational forces within the cosmic web. And clusters of galaxies, the largest gravitationally bound structures in the universe, continue to grow through the accretion of smaller galaxies and dark matter. Ultimately, the universe we observe today, with its spectacular galaxies and intricate structures, is a testament to the power of gravity acting on the subtle, initial density fluctuations that arose from the Big Bang. It's a remarkable demonstration of how simple physical laws, amplified over vast stretches of time and space, can give rise to the most complex and beautiful structures imaginable. The universe, born from a single, explosive moment, has become a tapestry of interconnected structures, all traceable back to those first, tiny ripples in the fabric of space-time. The universe, just a few 100 million years after the Big Bang, wasn't the smooth, featureless expanse we sometimes picture. The slight, almost imperceptible variations in density, those tiny ripples amplified over time, had begun to coalesce. These weren't gentle curves anymore. They were gravitational wells, regions where a little extra matter accumulated, pulling in more and more material from the surrounding space. The universe was becoming increasingly uneven, and at the heart of this change were the beginnings of something extraordinary: the first stars. These weren't the delicate, sun-like stars that would eventually dot the cosmos. Instead, they were behemoths, born from the most concentrated pockets of this leftover material. Their formation was a brutal, beautiful dance of gravity and nuclear fusion, a process unlike anything we see today. The density fluctuations, amplified by gravity, continue to draw in surrounding gas, mostly hydrogen and helium, remnants of the Big Bang's initial expansion. As more and more gas accumulated, the gravitational pull intensified, accelerating the rate of accretion. These nascent stars, dubbed population III stars, were incredibly massive, ranging from perhaps 100 to 1,000 times the mass of our Sun. This immense size was crucial to their formation. The stronger the gravity, the higher the core pressure became. This intense pressure triggered a reaction far more energetic than anything we experience on Earth: nuclear fusion. Hydrogen atoms began to smash together at astonishing speeds, fusing to create helium, releasing tremendous amounts of energy in the process. This energy radiated outwards, pushing back against the inward pull of gravity, establishing a precarious equilibrium. The fusion process within these first stars was extraordinarily efficient. Because the material was so dense, the conditions were perfect for rapid, runaway reactions. The helium produced from the initial hydrogen fusion then itself started to fuse, creating heavier elements like oxygen and neon. It was a cascade of nuclear reactions, each stage releasing more energy and transforming the star's core. These stars weren't burning steadily. They were exploding and collapsing repeatedly, a chaotic but remarkably effective way to generate enormous amounts of light and heat. The light emitted by these population III stars was intensely blue due to the extreme temperatures generated by the rapid fusion. They blazed with a ferocity unknown to later stars. These massive stars had incredibly short lifespans, perhaps only a few million years before collapsing in spectacular supernovae. Their existence was a temporary stage in the universe's evolution, a period of intense stellar activity that profoundly shaped the surrounding environment. The supernovae resulting from these first stars weren't gentle, fading events. They were catastrophic explosions, scattering the heavy elements they had created throughout the cosmos. This isn't merely a poetic description. It's a fundamental process in the universe's history. The elements heavier than helium, carbon, oxygen, nitrogen, iron didn't exist in significant quantities before these supernovae. They were forged within the cores of these massive stars, and then violently dispersed by the explosions. These dispersed elements became the building blocks for the next generation of stars, and eventually, for planets like our own. It's important to understand that these first stars weren't simply star factories. They were also cosmic recyclers, taking what was left over from the Big Bang and transforming it into the components of the universe we see today. The supernovae enriched the surrounding interstellar medium, creating a richer, denser environment ready to seed the formation of subsequent generations of stars. The process of stellar birth and death, driven by gravity and fusion, continued with each generation of stars becoming slightly smaller and living longer. The heavier elements produced by each supernova were incorporated into the next batch of stars, gradually shifting the composition of the universe. This cycle of stellar creation and destruction, repeated countless times over billions of years, has been the engine driving the evolution of the cosmos. Interestingly, the sheer brightness of these first stars likely had a significant impact on the surrounding regions. They emitted so much ultraviolet light that it likely suppressed the formation of molecular hydrogen, which is essential for star formation. This means that the rate of star formation itself was initially limited, creating a feedback loop. Fewer stars meant less heavy element production, which then allowed for more star formation. It's a complex, interwoven system, a delicate dance governed by gravity, energy, and the fundamental laws of physics. The eventual demise of these gigantic stars wasn't just about releasing energy. It was about fundamentally changing the universe's chemistry. They weren't just burning fuel. They were actively participating in the formation of the elements that would ultimately allow for the creation of planets, and perhaps, one day, life. The seeds of our own existence were sown in the intense light and violent death of these colossal stars, the first true beacons in the newborn universe. Scientists continue to study these population III stars through simulations and theoretical models, attempting to reconstruct their properties and understand the details of their formation and evolution. While direct observation remains incredibly challenging due to their immense distances and the intervening dust and gas, the evidence strongly suggests that these massive, early stars played a critical role in shaping the universe as we know it, leaving behind a legacy of heavy elements and paving the way for the galaxies and stars that followed. The universe, just a few 100 million years after the Big Bang, wasn't the serene expanse we see today. It was a turbulent, unbelievably hot and dense soup of hydrogen and helium, remnants of the initial burst of energy and the subsequent nuclear reactions. This wasn't a uniform mixture. Subtle differences in density, amplified over time, were starting to coalesce. Within these denser regions, gravity began its relentless work, pulling in more and more of the surrounding material. These accumulating clouds of gas weren't like anything we see in our own galaxy. They were incredibly massive, perhaps hundreds of times the mass of our sun, and composed almost entirely of primordial hydrogen and helium. These were the nascent seeds of what would become the first stars, designated population III stars. These early stars were fundamentally different from the ones born in galaxies like our own. They lacked the heavier elements, carbon, oxygen, iron, that make up the vast majority of stars today. The Big Bang itself produced only hydrogen and helium. The processes that forged these heavier elements, nuclear fusion within the cores of stars, were simply unavailable in this early universe. It's like trying to bake a cake without flour or sugar. The ingredients just weren't there. Their existence depended entirely on the raw materials that were present from the beginning, the very first elements created in the universe's infancy. Because of this lack of heavier elements, the fusion processes within population III stars were drastically different. The core temperatures were astonishingly high, often reaching tens of millions of degrees Celsius. This intense heat meant that the fusion reactions were incredibly rapid, almost runaway in some cases. The hydrogen nuclei didn't just combine to form helium. They underwent a series of reactions that produced lithium, a very light metal, but also created a vast amount of energy in the form of photons light. These weren't gentle, steady glows. They were blindingly brilliant, intensely energetic flashes. The characteristics of these stars also dictated their lifespans. They burned through their fuel at an unprecedented rate. Because the core temperature was so high and the fuel so readily available, the fusion process was incredibly efficient, but also incredibly short-lived. These stars lived only a few million years, perhaps even less in some cases. This rapid consumption of fuel distinguishes them dramatically from the long-lived giants found in galaxies like the Milky Way, which can shine for billions of years. Furthermore, because they were so massive and burned so intensely, the outer layers of these stars were constantly being stripped away in powerful stellar winds. These winds weren't just streams of gas. They were streams of charged particles moving at enormous speeds, carrying away vast quantities of hydrogen and helium. The stellar winds from population III stars were far more energetic and disruptive than anything we observe today. The immense energy released by these stars had a profound impact on the surrounding intergalactic medium, heating it to incredibly high temperatures. The intense radiation from these first stars also played a crucial role in reionizing the neutral hydrogen that remained after the recombination epoch. While recombination had established a transparent universe, the radiation from these newly born stars was powerful enough to strip electrons from hydrogen atoms, once again creating a plasma, a soup of free electrons and nuclei. This process of reionization continued for a considerable amount of time, gradually transforming the universe from a neutral state back into the ionized state we see today. As these massive population III stars reached the end of their extraordinarily brief lives, they experienced a spectacular and violent demise. They couldn't undergo the normal processes of a star's death, such as forming a planetary nebula or a white dwarf. Instead, they simply collapsed under their own immense gravity, triggering incredibly powerful supernova explosions. These weren't the gentle, beautiful supernovae associated with later generations of stars. They were far more energetic, releasing enormous amounts of energy and heavy elements into the surrounding space. These supernovae were critical. The heavy elements forged within the cores of these dying stars and subsequently dispersed during their explosive deaths became the building blocks for the next generation of stars, population II, and eventually, population I stars. It's a cycle of creation and destruction, a cosmic recycling process powered by the energy of the first stars. The remnants of these ancient supernovae seeded the universe with the materials necessary for the formation of planets, and ultimately, for the emergence of life. The study of population III stars is incredibly challenging because they are, by definition, extremely rare and incredibly distant. We haven't directly observed any of them. Instead, scientists use sophisticated computer simulations, incorporating our understanding of physics and cosmology to recreate the conditions of the early universe and model the formation and evolution of these first stars. Through these models, we can gain a deeper appreciation for their importance in shaping the cosmos, a legacy etched in the very fabric of the universe. Their brief but powerful existence marked a pivotal moment, laying the groundwork for the galaxies and stars we see around us today. The universe, in its immediate aftermath of the Big Bang, wasn't the relatively smooth, expanding space we understand today. Instead, it was a supremely energetic, unbelievably dense soup, a plasma. This plasma wasn't just a collection of gas. It was a sea of free electrons and ions, all buzzing with energy from the intense heat left over from the creation of everything. This state, utterly ionized, meant that almost every atom had lost its electrons, leaving behind a chaotic, swirling mixture of positively charged nuclei and negatively charged electrons. It was a state of incredible transparency. Light, including ultraviolet light, traveled almost unimpeded through this dense medium. This early universe was effectively a giant, glowing fog. As the universe continued to expand, it also continued to cool. This cooling was crucial because it allowed gravity to become the dominant force, pulling matter together in a process we've already begun to understand: the clumping of density fluctuations. The first generation of stars, born from the collapsing clouds of gas and dust, were incredibly bright and short-lived. They shone with ferocious intensity, emitting vast amounts of ultraviolet radiation. These early stars were particularly significant because their radiation was intensely energetic, capable of stripping electrons from atoms in the surrounding plasma. The process of stripping electrons from atoms is what we now call photoionization. When a photon, a particle of light, strikes an atom, it can transfer enough energy to knock an electron loose. This isn't just a gentle nudge. It's a forceful ejection, transforming the atom from a neutral state into a plasma again. Think of it like repeatedly hitting a ball against a wall. Eventually, the ball will bounce away with enough force to change its trajectory. The early universe was filled with these intensely luminous stars, constantly bombarding the surrounding plasma with their ultraviolet light. These stars were the initial agents of reionization. Their radiation was so powerful that it overcame the resistance of the neutral hydrogen and helium that had previously permeated the early universe. As the radiation interacted with the atoms, it repeatedly stripped electrons, gradually transforming the plasma back into a state of ionization. However, reionization wasn't a quick or uniform process. The distribution of these first stars wasn't perfectly even. Some regions of space were significantly denser than others, containing far more massive stars than others. These denser regions were the first to be reionized, effectively acting as local ignition points. The ionization spread outwards from these points, like ripples in a pond, gradually affecting the surrounding plasma. It's important to understand that this wasn't a single event, but rather a protracted, complex interaction between radiation and matter. The timeline of reionization is still being refined by astronomers, and there are ongoing debates about precisely when it occurred. Current estimates suggest that reionization began roughly 380,000 years after the Big Bang. This period is known as the Epoch of Reionization, and it represents a profound shift in the universe's composition and properties. Before this epoch, the universe was opaque to ultraviolet light. After, it became transparent. This transparency allowed the first faint light from galaxies to finally travel across the cosmos, a testament to the power of these early stars. The process of reionization wasn't solely driven by the radiation from the first stars. Dark matter, the invisible substance that makes up a significant portion of the universe's mass, also played a role. While dark matter doesn't directly interact with light, its gravitational influence amplified the density fluctuations, creating pathways for radiation to travel more efficiently. These pathways facilitated the ionization process, contributing to a more rapid and widespread transformation. As reionization proceeded, the universe transitioned from an opaque, neutral plasma to a gradually more transparent state. This transition fundamentally changed the way the universe looked and behaved. The ability of light to travel freely allowed the formation of the first large-scale structures, such as galaxies and galaxy clusters, to occur more readily. Without reionization, the universe would have remained a chaotic, opaque plasma, incapable of supporting the structures we observe today. The final stages of reionization were particularly intense, driven by the formation of an increasingly large number of galaxies. These galaxies, formed from the merging of smaller proto-galaxies, became the dominant sources of ultraviolet radiation, effectively completing the ionization process. It's a remarkable sequence of events, driven by the interplay of gravity, nuclear fusion, and the relentless energy of light. Scientists study the cosmic microwave background, CMB, the afterglow of the Big Bang, to understand the conditions that existed in the early universe. The patterns of temperature fluctuations in the CMB provide clues about the ionization state of the universe at different times. By analyzing these patterns, researchers can reconstruct the history of reionization, piecing together the story of how the universe transitioned from a chaotic plasma to the relatively ordered structure we inhabit today. It's a story etched in the very fabric of space-time, a cosmic saga of light, matter, and the relentless march of time. The period immediately following the Big Bang wasn't a uniformly bright, hot expanse, despite what some early models suggested. Instead, the universe was a tangled, opaque soup. Hydrogen and helium, the primary elements forged in the initial moments, were constantly interacting with each other, absorbing almost all of the ultraviolet light that tried to escape. This created a cosmic fog, a dense plasma where photons, the particles of light, couldn't travel very far without being scattered. It was like trying to see through a thick, swirling snowstorm. This state persisted for hundreds of millions of years, a period we call the Dark Ages. Then, something dramatic began to unfold: reionization. Understanding exactly how reionization happened and the precise dynamics involved has been a huge challenge for cosmologists. It's not a simple, single event. Instead, it was a gradual, complex process influenced by many factors, and the techniques we use to study it are extraordinarily powerful. At the heart of our attempts to understand this transformation are computer simulations, vast, intricate models that attempt to recreate the conditions of the early universe. These simulations aren't just guesses. They're built on our best understanding of physics, constantly refined as we gather new observational data. One of the most common types of simulation focuses on the growth of structure, the way gravity pulled together small fluctuations in the density of the early universe into larger and larger clumps of matter. These initial fluctuations, seeded by quantum mechanical effects in the very early universe, weren't perfectly uniform. Some regions had slightly more matter than others. As gravity acted on these overdensities, they began to collapse, forming the first proto-galaxies, which would eventually evolve into the galaxies we see today. Simulations track the evolution of these structures, modeling the interplay of gravity, hydrodynamics, the physics of fluid flow, and radiative transfer, how photons interact with matter. A crucial element within these simulations is the inclusion of the first generation of stars. As discussed in earlier parts, these population III stars were incredibly massive, far larger and hotter than any stars we see today. Their intense ultraviolet radiation played a pivotal role in reionization. The simulations don't simply treat these stars as point sources of light. Instead, they model their internal processes, nuclear fusion, energy transport, and the production of heavy elements, with remarkable detail. The models consider how this radiation was absorbed and re-emitted by the surrounding hydrogen and helium plasma. However, the role of the first stars alone couldn't fully explain the observed timescale of reionization. Simulations initially struggled to produce reionization quickly enough. It turned out that the rate at which these early galaxies formed and their subsequent evolution was critical. The models were modified to incorporate a more realistic depiction of galaxy mergers, where smaller galaxies collided and merged, creating larger, more efficient sources of radiation. These mergers dramatically increased the number of bright, young stars, contributing to the reionization process. Another important factor influencing the simulation results was the inclusion of feedback mechanisms. When massive stars die, they release tremendous amounts of energy in the form of supernovae. This energy heated the surrounding gas, pushing it outwards and preventing it from collapsing further. Simulations now incorporate these feedback processes, reflecting the dynamic interplay between star formation and the surrounding interstellar medium. Without accounting for this feedback, simulations consistently underestimated the efficiency of reionization. Furthermore, scientists use sophisticated radiative transfer codes within the simulations. These codes meticulously track the paths of photons as they travel through the universe, taking into account scattering, absorption, and emission processes. The results of these calculations provide a detailed picture of how the early universe looked to an observer at any given time. These visualizations, often rendered as beautiful, swirling clouds of color, offer compelling insights into the complex dynamics of the reionization epoch. Different simulations use different approximations of radiative transfer, and their results can vary significantly. The resolution of the simulation, The detail at which it models the universe also plays a vital role. Finer resolutions typically lead to more accurate results, but demand significant computational power. Current simulations are pushing the limits of what's possible, utilizing supercomputers to model the universe at increasingly higher resolutions and with more sophisticated physical models. These models are constantly being refined with new observational data from telescopes like the James Webb Space Telescope. JWST, with its unprecedented ability to observe infrared light, is providing a crucial window into the distant reionization era, allowing astronomers to directly probe the properties of the first galaxies and the ionizing radiation they emitted. The data from JWST is feeding back into the simulations, creating a powerful iterative process of observation and modeling. The ultimate goal is to create a fully self-consistent model of reionization, one that accurately reproduces all the observational data we have. This is a monumental task, demanding ongoing advancements in both theoretical modeling and observational capabilities. While a complete understanding remains elusive, the simulations and models currently being developed are bringing us closer to unlocking the secrets of this transformative epoch, revealing the dawn of the universe as we know it. The universe, just a few 100 million years after the Big Bang, was a dramatically different place than it is today. It wasn't yet filled with the familiar spiral galaxies we see stretching across the night sky. Instead, it was dominated by a hazy soup of hydrogen and helium, a diffuse plasma constantly interacting with the faint glow left over from the Big Bang itself, the cosmic microwave background radiation. For a long time, astronomers relied on telescopes like the Hubble Space Telescope to peek back into this early era, but Hubble's vision was limited by the way starlight and other wavelengths of light interacted with the intervening gas and dust. It was like trying to see a distant forest through a thick fog. Hubble could detect the light from galaxies, but the light was often smeared and distorted, making it difficult to understand their precise shapes and, crucially, their formation processes. Then in December 2021, something remarkable happened. The James Webb Space Telescope, or JWST as it's affectionately known, began its mission, and suddenly the early universe became far clearer. JWST's secret weapon is its ability to observe infrared light. While Hubble is primarily designed to see visible light, JWST's instruments are incredibly sensitive to infrared wavelengths. This is because the cosmic microwave background radiation has been redshifted, stretched out, by the expansion of the universe. The lower energy wavelengths of infrared light are less affected by this stretching, allowing them to penetrate the dense clouds of gas and dust that obscured the early universe from Hubble's perspective. It's like having a special pair of glasses that allows you to see through the fog, revealing details that were previously hidden. The first observations from JWST focused on the most distant galaxies ever observed, galaxies that existed when the universe was only about 300 million years old. These weren't the grand, mature galaxies we see today. They were incredibly small, irregular, and intensely bright. These early galaxies were found using a technique called dropout. where astronomers looked for wavelengths of light that the galaxies emitted strongly, but that were absorbed by the intervening gas. JWST, with its infrared capabilities, could see the light that passed through the dust, revealing these hidden galaxies. One of the most striking discoveries was the prevalence of these extremely bright, compact galaxies. Initially, scientists weren't entirely sure what to make of them. The models of galaxy formation at this time predicted that galaxies should be growing gradually, merging with smaller ones, and becoming larger and more organized over time. But JWST was finding these tiny, intensely bright objects as if they were being born and dying incredibly quickly. Further analysis of the light from these galaxies revealed something even more surprising. They were undergoing intense bursts of star formation. These galaxies weren't slowly building up their mass. Instead, they were experiencing periods of incredibly rapid growth, fueled by the creation of hundreds, even thousands of massive, hot, and short-lived stars. Essentially, a stellar explosion occurring within the galaxy itself. These stars, belonging to what are sometimes referred to as population III-1 or population Ia, are considerably more massive than any stars we observe today, and their existence provides crucial clues about the conditions in the early universe. The light from these galaxies also contained chemical signatures, evidence of the elements that were forged inside these newborn stars and then scattered throughout the surrounding gas. JWST detected the presence of heavier elements, such as oxygen and carbon, at surprisingly high levels for such young galaxies. This suggests that the first generations of stars weren't just burning hydrogen and helium. They were also processing and recycling these elements, enriching the surrounding interstellar medium. The detailed observations have challenged some long-held assumptions about galaxy formation. It appears that the process was far more chaotic and violent than previously thought. These early galaxies weren't following a smooth, predictable trajectory of growth. They were experiencing periods of intense activity, followed by periods of relative quiescence. This rapid burst of star formation was likely triggered by gravitational instabilities, small fluctuations in density that caused regions of gas to collapse under their own gravity. These collapsing regions then triggered the formation of stars, which in turn amplified the gravitational effects, leading to even more rapid star formation. JWST's observations have also provided crucial information about the reionization epoch, the period when the universe transitioned from being a neutral plasma to an ionized plasma. The intense ultraviolet radiation emitted by these young, massive stars played a key role in this process, stripping electrons from hydrogen atoms and ionizing the surrounding gas. The telescope's ability to see through the dust has allowed scientists to trace the path of this radiation, mapping out the regions where the reionization process was taking place. As JWST continues to gather data, astronomers are refining their models of galaxy formation and the reionization epoch. The telescope's unparalleled sensitivity and resolution are providing a remarkably detailed picture of the universe's infancy, allowing scientists to test and refine our understanding of how galaxies formed and evolved in the first few 100 million years after the Big Bang. It's a truly groundbreaking era for cosmology, offering a window into the very origins of the structures we see today. The data isn't just confirming existing theories, it's generating entirely new questions and possibilities about the evolution of the universe. The universe, as we understand it today, is a vast and expanding place, filled with galaxies, stars, and planets. But even in the moments immediately following the Big Bang, a hidden drama was unfolding, a drama not of light, but of ripples in space-time itself. Scientists have long theorized that the incredibly violent expansion of the universe in its earliest stages, a period known as inflation, would have generated gravitational waves. These waves aren't like the water waves you might see at the beach. They're disturbances in the very fabric of space and time, propagating outwards at the speed of light, carrying information about the universe's infancy. For a long time, the existence of these primordial gravitational waves was purely theoretical. The inflationary epoch, a period lasting a tiny fraction of a second, was characterized by exponential expansion. During this time, the universe underwent an unbelievably rapid increase in size, smoothing out any initial irregularities and stretching space itself to enormous scales. This rapid stretching wasn't just about the universe growing. It was accompanied by the creation of these gravitational waves. Think of it like shaking a bedsheet. The faster you shake it, the larger the ripples become, and the more energy is transferred across the surface. The Big Bang was an unbelievably intense shaking event, and the resulting gravitational waves were immensely powerful. Detecting these waves is incredibly challenging. Because they were generated during such a formative period, the waves have been stretched to incredibly long wavelengths, and their amplitude, the amount of distortion they cause, has been reduced significantly due to the expansion of the universe itself. They are, essentially, ghosts of the Big Bang, faint echoes of an event that happened almost 14 billion years ago. Scientists have been tirelessly searching for these subtle signals, employing sophisticated instruments designed to detect minute changes in space-time. The primary method being utilized is through the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo. These observatories aren't telescopes in the traditional sense. They don't collect light. Instead, they use lasers and mirrors to precisely measure changes in distance. LIGO consists of two L-shaped detectors, each with arms nearly 4 kilometers, 2.5 miles long. A laser beam is split into two, and each beam travels down one arm of the L before being reflected back by a mirror and recombined. Any passing gravitational wave will slightly alter the lengths of these arms, causing a minuscule shift in the interference pattern of the recombined laser beams. This tiny change is detected by incredibly sensitive sensors. The Virgo detector, located in Italy, operates in a similar fashion, providing a wider geographic coverage and allowing for cross-validation of detections. Furthermore, a future space-based detector, LISA, Laser Interferometer Space Antenna, will be even more sensitive, capable of detecting lower frequency gravitational waves that are inaccessible to ground-based observatories. LISA will consist of 3 spacecraft arranged in a triangular formation, separated by millions of kilometers. In 2015, LIGO made the groundbreaking detection of gravitational waves originating from the merger of 2 black holes. This was the first direct detection of these elusive ripples in spacetime, confirming a key prediction of Einstein's theory of general relativity. The signals were unmistakable, a specific pattern of changes in the laser beams that could only be explained by the passage of gravitational waves. This detection opened a completely new window onto the universe, allowing us to study cataclysmic events like black hole mergers that were previously invisible. However, the implications extend far beyond simply confirming the existence of gravitational waves. Scientists are actively searching for other sources, including the merger of neutron stars and potentially the very beginning of the universe itself. If gravitational waves were generated during inflation, they could provide invaluable insights into the energy scale and dynamics of that period. The amplitude of these primordial waves would be directly related to the energy density of the early universe. Specifically, scientists are looking for a particular type of gravitational wave signal called the B-mode polarization of the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, a faint, uniform radiation that permeates the entire universe. During inflation, quantum fluctuations in the early universe were stretched to enormous scales, creating tiny density variations. These variations would have generated gravitational waves, and as the waves propagated through space, they would have imprinted a subtle polarization pattern on the CMB. Detecting this polarization pattern would be like looking at the fingerprints of inflation, allowing us to probe the conditions of the universe in its earliest moments. The detection of the B-mode polarization would provide strong evidence for the theory of inflation, and it could even reveal the precise energy scale at which inflation occurred. Furthermore, understanding the statistical properties of these primordial gravitational waves could offer clues about the fundamental laws of physics that govern the universe's infancy. It's a remarkably powerful tool for understanding the very origins of space and time. The ongoing and future observations with LIGO, Virgo, and LISA hold tremendous promise for unraveling some of the biggest mysteries in cosmology. They are offering a completely new perspective on the universe, one that complements and extends our understanding based on light and other forms of electromagnetic radiation. The detection of gravitational waves is not just a scientific triumph. It is a fundamental shift in our ability to explore the cosmos, providing a direct connection to the universe's earliest moments. The universe, after the initial burst of the Big Bang, wasn't just expanding. It was expanding at an accelerating rate. This wasn't a gentle, gradual stretching like a balloon inflating slowly. It was a furious, ever-quickening process, and understanding how fast it was expanding became one of the most crucial quests in modern cosmology. The key to unlocking this rate was a value known as the Hubble constant, a deceptively simple name for a profoundly complex measurement. Initially, Edwin Hubble in the late 1920s made a groundbreaking observation. He meticulously studied the light from distant galaxies, analyzing a phenomenon called redshift. Redshift, in this context, isn't about colors changing. It's a shift of light waves towards the red end of the spectrum. Hubble discovered that almost all galaxies were redshifted, and the amount of redshift was directly proportional to their distance from us. This meant that the further away a galaxy was, the faster it appeared to be moving away. He plotted these distances against their redshifts, creating a simple graph, and found a linear relationship. He proposed that the Hubble constant, often represented by the letter h0, was the slope of this line. Essentially, it represented the velocity at which galaxies were receding from us per unit distance. His initial estimate, around 200 kilometers per second per megaparsec, was a pivotal step, but it quickly became apparent that the value wasn't as straightforward as it first appeared. A megaparsec is a unit of distance. 1 megaparsec is approximately 3.26 million light years. So, Hubble's constant essentially stated that for every 3.26 million light years a galaxy is away from us, it's moving away at 200 kilometers per second. However, precision measurements revealed that Hubble's initial estimate was significantly off. The discrepancy opened a fascinating and somewhat frustrating debate that continues to this day. What is the true value of h0? Several methods emerged for measuring this expansion rate, each with its own set of assumptions and potential limitations. One approach relies on observing Cepheid variable stars in distant galaxies. Cepheids are pulsating stars whose brightness changes predictably with their pulsation period. This period directly relates to their intrinsic luminosity, allowing astronomers to calculate their distance based on their observed brightness. By measuring the redshifts of galaxies hosting these Cepheids, astronomers could then determine their distances and velocities, refining the estimate of h0. Another technique utilizes type Ia supernovae, another class of exploding stars with remarkably consistent peak brightnesses. These supernovae serve as standard candles, allowing astronomers to measure distances across vast cosmic scales. By comparing the observed brightness of type Ia supernovae with their known intrinsic luminosity, distances can be accurately calculated. The redshift of the galaxies hosting these supernovae further confirms the expansion rate. However, the different measurement techniques began to yield increasingly different results. Measurements based on the distance ladder, built up from Cepheids to supernovae and beyond, consistently pointed to a value of around 73 kilometers per second per megaparsec. Simultaneously, observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, provided an independent estimate, suggesting a value closer to 67 kilometers per second per megaparsec. These discrepancies were significant, almost 10 kilometers per second per megaparsec. This disagreement sparked intense scrutiny and a growing sense of bewilderment. The value of h0 is deeply intertwined with our understanding of the universe's age and composition. A different value for H0 would have profound implications for everything from the timeline of galaxy formation to the ultimate fate of the universe. Initially, the debate was largely dismissed as a systematic error, a flaw in one or more of the measurement techniques. However, the persistent disagreement, despite repeated attempts to refine the observations and correct for potential biases, became impossible to ignore. The leading explanation for the tension revolves around the concept of dark energy. Dark energy is a mysterious force that makes up roughly 68% of the universe's total energy density. Its effect is to cause the expansion of the universe to accelerate. If the expansion is accelerating, then the rate at which distant objects appear to be receding from us is greater than what would be predicted by a universe expanding at a constant rate. The different measurement techniques are inherently sensitive to different aspects of this accelerated expansion, leading to the observed discrepancies. Furthermore, the possibility of local effects influencing the expansion rate, such as the gravitational pull of large-scale structures in our region of the universe, has been considered, though these explanations haven't gained widespread acceptance. The ongoing efforts to precisely measure H0, using increasingly sophisticated instruments and techniques, including space-based interferometry, are a crucial part of the puzzle. These efforts aim not just to determine the value of H0, but also to understand the nature of dark energy and the dynamics of the expanding universe. The quest to nail down the Hubble constant is a testament to the power of scientific inquiry. It's a reminder that even seemingly straightforward measurements can be incredibly complex when dealing with the vastness and intricacies of the cosmos. The journey to solve this mystery is shaping our understanding of the universe's fundamental properties and continues to drive innovation in observational astronomy and cosmology. The universe in its infancy wasn't just expanding, it was doing so at an astonishing rate. This expansion, initially subtle, carried with it a peculiar effect on light traveling from distant objects. This effect, known as cosmological redshift, became one of the most compelling pieces of evidence supporting the Big Bang theory and our understanding of the universe's evolution. It's a story told through stretching light, a fundamental property of space itself. Consider a simple analogy. Imagine a car driving away from you. As it speeds past, the sound of its horn seems to lower in pitch, doesn't it? This is because the sound waves are being stretched as they travel away from you. Light behaves similarly. The expansion of the universe is like an invisible fabric stretching, and as light waves pass through this expanding space, they get elongated. This lengthening, this change in wavelength, is what we observe as redshift. Specifically, the light from distant galaxies isn't just moving away from us, it's being stretched. The longer the light travels through the expanding universe, the more it's stretched. The wavelength of the light gets pushed towards the red end of the spectrum, hence, redshift. It's not that the light itself is changing color, but rather that the space between us and the light source is growing, causing the wavelength to increase. The degree of redshift is directly proportional to the distance of the object. The farther away a galaxy is, the more its light has been stretched, and therefore the greater the redshift. This relationship is described mathematically by Hubble's law, a remarkably simple but profound equation. Velocity equals Hubble constant distance. The Hubble constant represents the rate at which the universe is expanding, a constant that astronomers are still working to precisely determine. Different measurements of the Hubble constant, based on different methods, yield slightly different values, leading to ongoing research and debate. Measuring redshift involves sophisticated instruments and careful analysis. Astronomers use spectrographs, devices that split light into its constituent colors, much like a prism. By examining the spectrum of light from a distant galaxy, they can identify the specific wavelengths that are present. A shift towards the red end of the spectrum signifies redshift. The amount of the shift is then used to calculate the galaxy's distance and its velocity, how fast it's moving away from us. It's not just the overall redshift that's significant. The shape of the redshift curve is also crucial. Redshift isn't a single, sharp peak. Instead, it's a continuous distribution of wavelengths, a smear across the spectrum. The precise shape of this smear provides information about the velocity distribution of galaxies, whether they're moving randomly or in a particular direction. The cosmic microwave background, CMB, that faint afterglow of the Big Bang we discussed in earlier parts, provides another invaluable tool for studying redshift. The CMB is incredibly uniform in temperature, but subtle variations in this temperature correspond to slight variations in redshift. These variations, imprinted in the CMB's temperature fluctuations, reflect the density fluctuations in the early universe, the seeds from which galaxies eventually formed. Analyzing these fluctuations allows astronomers to reconstruct the universe's evolution from the very beginning. Furthermore, the study of quasars, incredibly luminous active galactic nuclei powered by supermassive black holes, relies heavily on cosmological redshift. Quasars are among the most distant objects we can observe, and their extremely high redshifts provide crucial data for understanding the conditions in the early universe and the formation of galaxies. The light from these distant quasars has traveled for billions of years, carrying with it information about the universe's state at various points in its history. The confirmation of cosmological redshift wasn't immediate. Early observations suggested a rapidly rotating universe, a concept that contradicted the prevailing understanding. However, the consistent observation of redshift across vast distances, coupled with the discovery of the expanding universe, first suggested by Edwin Hubble in the 1920s, firmly established redshift as a cornerstone of cosmology. It's important to recognize that cosmological redshift isn't just a phenomenon related to the universe's expansion. There are other mechanisms that can cause redshift, such as the Doppler effect, which explains why the pitch of a siren changes as it approaches or moves away from you. However, in the context of cosmology, cosmological redshift is the dominant and most significant contributor to the observed redshift of distant objects. The ongoing research into cosmological redshift is pushing the boundaries of our understanding. Scientists are utilizing new telescopes, like the James Webb Space Telescope, to observe even more distant galaxies and quasars, gathering data at unprecedented levels of detail. They're also developing more sophisticated models to refine our measurements of the Hubble constant and to better understand the dynamics of the expanding universe. The story of cosmological redshift is far from complete. It's a dynamic, evolving narrative shaped by observation and theoretical advancements. It's a testament to human curiosity and our persistent quest to unravel the mysteries of the cosmos. The story of the Big Bang, as we understand it, rests upon a remarkably successful framework known as the Standard Cosmological Model. It's not a single, simple answer, but rather a complex and beautifully interwoven set of ideas, built over decades of observation and increasingly precise measurements. At its heart, the Lambda-CDM model proposes a universe that began with an incredibly hot, dense state and has been expanding and cooling ever since. The lambda part stands for the cosmological constant, representing dark energy, a mysterious force driving this expansion at an accelerating rate. CDM refers to cold dark matter, the dominant form of matter in the universe that doesn't interact with light and therefore remains invisible to us. The model's foundation rests on several key assumptions, all supported by a growing body of evidence. One fundamental assumption is the principle of homogeneity, which suggests that the universe looks roughly the same from any point in space. On a very large scale, the distribution of galaxies and the overall structure of the cosmos appear consistent, regardless of where you happen to be observing from. Another crucial assumption is isotropy. The universe is equally likely to look the same in all directions. This doesn't mean every galaxy looks identical, but statistically, there's no bias towards any particular direction. Then there's the assumption of a flat geometry for the universe. This isn't about the universe being literally flat like a sheet of paper, but rather that its overall curvature is zero. This is primarily determined by measuring the distances to faraway objects, particularly Type Ia supernovae, exploding stars that act as incredibly consistent standard candles because of their predictable brightness. These measurements, combined with the observed redshift, strongly suggest that the universe is geometrically flat. Beyond these fundamental assumptions, the Lambda-CDM model incorporates a detailed timeline of the universe's evolution. It predicts that the early universe was dominated by a plasma of hot, ionized particles. As the universe expanded and cooled, these particles combined to form neutral hydrogen and helium, the raw ingredients for the first stars and galaxies. The model also predicts the formation of large-scale structures, like galaxy clusters and superclusters, driven by tiny initial density fluctuations amplified by gravity over billions of years. These fluctuations, imprinted in the cosmic microwave background, CMB, provide a snapshot of the universe shortly after the Big Bang. However, the standard cosmological model isn't without its critics and unresolved puzzles. One of the most persistent issues is the nature of dark matter. While the model hinges on its existence to explain the rotation curves of galaxies and the structure formation, we still don't know what dark matter is. Numerous experiments have searched for weakly interacting massive particles, WIMPs, a leading dark matter candidate, but so far without conclusive detection. Alternatives are being explored, including axions and sterile neutrinos, but each comes with its own set of challenges. Another significant challenge arises from the discrepancies observed in the distribution of galaxies on smaller scales. Simulations based on the lambda-CDM model often predict a greater abundance of small satellite galaxies orbiting larger galaxies than what we actually observe. This missing satellite problem suggests that our understanding of dark matter self-interaction, or the processes governing small-scale structure formation, may be incomplete. Furthermore, some analyses of the CMB have revealed slight statistical anomalies, known as lithium problems, which question the precise values predicted by the model for the abundance of lithium-7. The accelerating expansion of the universe, driven by dark energy, also presents a profound mystery. The cosmological constant, as represented by lambda, is extraordinarily difficult to explain theoretically. Its predicted value is vastly larger than what is observed, a discrepancy known as the cosmological constant problem. Many physicists are searching for alternative explanations for dark energy, such as quintessence, a dynamic, evolving field of energy, but no single theory has yet gained widespread acceptance. Furthermore, the model struggles to explain the very initial conditions of the universe, what triggered the Big Bang itself. It describes the evolution after the initial moment, but doesn't provide a fundamental explanation for why it happened. It's a remarkable achievement, this model, successfully explaining a vast amount of cosmological data, but it's understood to be a best-guess framework, continually refined and tested as new observations emerge. The ongoing quest to understand the universe's origins and its ultimate fate continues, driven by observations from space telescopes, ambitious ground-based surveys, and theoretical advances. It's a testament to the enduring power of human curiosity and our dedication to unraveling the grandest mysteries of existence. The model, in its current form, represents a stunning success, but the universe, as always, holds further secrets waiting to be discovered. The prevailing picture of the universe's birth, the Big Bang, has been remarkably successful in explaining a vast array of observations. It describes a universe expanding from an incredibly hot, dense state, cooling and evolving over billions of years into the cosmos we see today. However, the very nature of that initial state and the mechanisms driving its evolution have remained a point of ongoing debate and exploration within the scientific community. For a long time, the Big Bang model, particularly the lambda-CDM model, presented a largely bottom-up story. It posited that everything from the smallest particles to the largest galaxies arose from the gradual cooling and dilution of the initial, unimaginably hot plasma. Tiny quantum fluctuations, amplified by inflation, seeded the formation of structure. The first atoms, then stars, then galaxies, all growing from relatively simple beginnings. But as cosmological research progressed, a compelling and radically different perspective began to emerge: top-down cosmology. The core difference between these approaches lies in their starting points. Bottom-up cosmology begins with an extremely hot, chaotic beginning and asks, how did things organize themselves from that state? It's like watching a huge pile of Lego bricks and wondering how they spontaneously assemble into a complex castle. Top-down cosmology, conversely, starts with a specific, predetermined outcome, a universe with a particular level of complexity, perhaps even with specific patterns or structures, and then asks, how could this have arisen from simpler precursors? It's as if you already have a beautiful, intricate snowflake and are trying to understand the conditions necessary for it to form, rather than beginning with a blank piece of ice. The roots of top-down cosmology can be traced back to the work of physicist Sir Roger Penrose in the 1960s and 70s. He proposed a radical idea that the universe isn't just expanding, it's also contracting in a cyclical manner. This wasn't a simple, straightforward contraction, but rather a highly complex, self-similar process, where the universe expands, then contracts, then expands again, each cycle becoming increasingly similar to the last. Crucially, Penrose suggested that the patterns we observe in the cosmos, the distribution of galaxies, the cosmic microwave background radiation, weren't just the result of random fluctuations. Instead, they were imprinted by the very structure of the contracting phase, acting like a kind of memory of the previous cycle. This concept, known as imprint cosmology, envisioned the universe emerging from a previous highly ordered state, a state where the fundamental laws of physics were perhaps different, or where the conditions were just right for a specific pattern to emerge. The Big Bang in this scenario wasn't a truly first moment, but rather a bounce, the transition point from a contracting phase to an expanding one. The observed uniformity of the cosmic microwave background, for example, wouldn't be a random occurrence, but the remnant of this pre-existing order. Another influential proponent of top-down cosmology is physicist Andre Lind. He developed a model based on eternal inflation. In this scenario, inflation, the period of incredibly rapid expansion in the early universe, never truly stops. Instead, it continues in different regions of space, creating an infinite number of bubble universes, each potentially with its own physical laws. Our observable universe would simply be one of these bubbles, emerging from a pre-existing, eternally inflating space. This doesn't necessarily imply a single, definite beginning, but rather a continuous process of creation and variation. The appeal of top-down approaches stems partly from their ability to address some of the puzzles that remain within the standard Big Bang model. For instance, the problem of the fine-tuning of the universe, why the fundamental constants of nature seem exquisitely calibrated to allow for the existence of stars, galaxies, and ultimately life, can be viewed differently. Instead of seeing these constants as the result of random chance, a top-down cosmology might suggest they were predetermined by the laws of the previous cycle. Similarly, the issue of dark energy, the mysterious force driving the accelerating expansion of the universe, could be interpreted as a consequence of the final state of the previous universe. Of course, neither top-down nor bottom-up cosmology enjoys universal acceptance. The standard Big Bang model remains the most widely supported, largely due to its strong observational backing and its ability to explain a vast range of phenomena. However, top-down approaches aren't seen as replacements for the standard model. Instead, they are often viewed as complementary frameworks, offering alternative perspectives on the very beginning of everything. They highlight the possibility that our universe might be part of a larger, more complex, and potentially cyclical structure, rather than a truly unique and isolated creation. The ongoing debate between these approaches is a testament to the inherent humility of science. The recognition that our understanding of the universe is always evolving, always subject to revision, as we gather new data and develop new theoretical tools. Perhaps ultimately, a synthesis of both bottom-up and top-down thinking will be needed to fully grasp the origins of our universe. A story that starts with a chaotic beginning and ends with a beautiful, intricate, and perhaps eternally repeating cycle. The beauty of it all is that the exploration itself, the striving to understand, is a journey without end. The observable universe, as we currently understand it, isn't an ending point, but rather a snapshot of a continuously unfolding story. The expansion that began with the Big Bang hasn't just continued, it's accelerating. This acceleration, driven by a mysterious force we call dark energy, is profoundly shaping the ultimate destiny of everything. We've established that the universe is vastly larger than the portion we can see, and that its geometry is remarkably flat, a detail crucial to predicting its future. However, that future is far from certain, a complex calculation reliant on the behavior of dark energy, a component we still struggle to fully comprehend. The sheer scale of the universe, combined with this accelerating expansion, points towards several potential outcomes, each with drastically different implications for the long-term fate of galaxies, stars, and eventually, everything within. One of the most frequently discussed scenarios is what's often called heat death. This isn't a fiery apocalypse, but a gradual, relentless dispersal of energy. As the universe expands, the density of matter decreases. Galaxies, already incredibly distant, will continue to drift further apart, becoming increasingly faint and unreachable. Star formation will eventually cease as the available gas and dust are depleted. Existing stars will burn out, leaving behind only stellar remnants, white dwarfs, neutron stars, and black holes. These remnants, though incredibly dense, will still radiate energy, albeit at lower and lower levels, eventually cooling down to absolute zero. This cooling process isn't instantaneous. It's a tremendously slow, ionic process. Over an unimaginable timescale, the universe will become a vast, cold, and nearly empty expanse. The remaining energy will be spread so thinly that no structures, no galaxies, no stars, no planets will exist. There will be no temperature gradients, no usable energy, and no possibility for any further activity. It's a state of maximum entropy, where everything is evenly distributed and nothing happens. The laws of physics will still operate, but they'll be entirely passive, governing a void of unimaginable proportions. The universe won't cease to exist, merely become a state of utter quiescence. It's a chillingly elegant, though profoundly desolate, vision. However, the nature of dark energy introduces another, far more dramatic possibility: the Big Rip. This scenario hinges on the assumption that dark energy isn't constant, but that its density actually increases over time. If this increase is rapid enough, it could lead to an exponential acceleration of the expansion. Initially, this might not seem alarming. Galaxies would still be moving apart. But as the expansion continues to accelerate, the gravitational forces holding together large structures, first galaxies, then galaxy clusters, then even individual galaxies, would become increasingly inadequate. Imagine a spiderweb stretching, with each strand representing a gravitational force. As the expansion continues, the strands become thinner and thinner until they snap. First, galaxies would be ripped apart, their stars scattered across the cosmos. Then the individual stars would be unbound, followed by the planets orbiting them. And finally, even the atoms themselves would be torn as the expansion overcomes the electromagnetic forces holding them together. All matter, reduced to its fundamental constituents, would be stretched to infinite lengths, a catastrophic dissolution of everything we know. This rip wouldn't be a sudden event, but a gradual disintegration, occurring over a period that, while immense, would ultimately end in complete annihilation. The likelihood of the Big Rip remains uncertain, largely dependent on the precise behavior of dark energy, something we are actively trying to understand through various cosmological observations. It's a dramatic outcome, a stark contrast to the slow, inevitable decay of heat death. The third potential fate, and one that presents a surprising, though somewhat circular, possibility, is the Big Crunch. This scenario is predicated on the idea that the expansion of the universe might eventually slow down and reverse. This wouldn't require a sudden, dramatic shift in dark energy, but rather a subtle change in the overall density of the universe. If the density of matter and energy were to increase over time, gravity would eventually overcome the expansion, causing the universe to contract. As the universe shrinks, galaxies would begin to collide, merging together to form larger and larger structures. The temperature would rise dramatically as the density increases. Eventually, everything, all matter, all energy would be compressed into an infinitely small point, a singularity, similar to the conditions that existed at the moment of the Big Bang. This singularity would then initiate a new Big Bang, and the cycle would begin again. This cyclic model, sometimes called the oscillating universe, suggests that the universe isn't destined for an ultimate end, but for an endless series of expansions and contractions. It's a fascinating idea, but it requires a deeper understanding of dark energy and the forces governing its behavior. While the observational evidence currently leans against a cyclic universe, the possibility remains open, particularly if our current understanding of dark energy is incomplete. Ultimately, the fate of the universe remains one of the greatest unsolved mysteries in science. The most likely scenario, heat death, is a slow, inevitable decline into a state of maximum entropy. However, the possibility of the Big Rip or the Big Crunch keeps the door open to a far more dramatic and uncertain future. The continued study of cosmology, the pursuit of understanding dark energy, and the gathering of observational data are all vital steps in unraveling this profound cosmic puzzle. Perhaps, in the distant future, humanity, or something entirely new, will possess the knowledge to definitively answer this question. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The echoes of the Big Bang have faded, returning the universe to a quiet stillness. Let your thoughts drift now, calm and unhurried as the cosmos releases its hold.